This video is going to be a common physics problem involving the conversion of mechanical energy to thermal energy. What we can see here is a problem where what we have on the right is this, it's kind of, it looks like almost like a dumbbell-shaped structure. On the bottom here, we have this area that's full of tiny little lead balls, and on the top here, kind of an empty space. So what's going to happen is as we rotate this, um, this device is just going to essentially, the lead balls are going to go to the top and they're going to fall down to the bottom. And what's going to happen during that time is certain amounts of their potential energy or kinetic energy are going to be converted into heat. Essentially, we just say that this is going to heat up. So the whole problem's here on the right, but basically what I'm going to do is just pick out the key parameters, and that is going to be the total mass of those lead balls, the heat, or the specific heat of the compound, as well as the gravitational constant and the 2.2 meters that I can see right here. So the question's asking us to find work. So what do we know about work? We know that work is equal to force times distance. And in this case, we know that the force that's being done is that due to gravity. And kind of the hint in the problem is that they tell us the acceleration due to gravity, and they tell us something is coming up to the top and then falling. So I'm going to go ahead and expand this force term to m times g, and that's going to be multiplied by d, and that's going to be our value for work. So then all I'm basically going to do is just plug in these numbers. So the mass is 2.5. The gravitational constant is 9.8. And the distance that they're falling is going to be 2.2. Now, these lead balls, when they're falling in the direction of gravity. Gravity is pointing down. The lead balls are falling down, so therefore work is going to be positive. There's also this cosine or sine of theta term that's at the end here. It's FD, I believe it's sine of theta. That might be cosine, but it doesn't matter in this case because it's just 180, so it's going to equal 1, or the angle 0. So it's just, this is definitely cosine of theta. So I go ahead and I just multiply these numbers out. I can do that pretty easily, and I'm going to find that my total work done by the system is going to be 53.9, and the units for work are joules, and we know it's joules because all the standard units went into this. We put mass in kilograms, gravity in meters per second squared, and our distance in terms of meters. So this next part here has us repeating the process 100 times. So if one repetition produced 53.9 joules, 100 repetitions is going to produce 100 times 53.9, which is going to give me 5,390 joules of work. And with that number, we're trying to figure out the theoretical cumulative temperature change after the 100 repetitions. So what we can see here is this is joules, so it's going to be the same unit that we use for heat. So what we can use is the equation Q is equal to mc delta T. And this delta T term is going to represent our cumulative temperature change. All right, so then again, we're just going to go ahead and put in these values here. So Q is brought down from the top. M is going to be the mass of these balls, which was 2.5. C is the specific heat, which is this number given up here, this 136 joules per kilogram Kelvin. And again, times delta T. And what I'm going to do is just simply divide both sides of these equations by 2.5 times 136. 2.5's cross, 136 cross, and go ahead and put that number into the calculator really quick, and we're going to find that this is equal to about 15.85 degrees Kelvin. And that's pretty much how you do that problem.